last talk. The speaker is Bao Vuong, and he's from Tom's State University. He is going to talk on Euclidean structure on trefoil knot with a bridge. So, wow.
Okay, thank you. So I will talk about the Euclidean structure on trefoil knot with a bridge. This is a joint work with Abrosimov, Mednykh, and Grunwald. Let me start with the definition of the two-bridge link. The two-bridge link L in the S3 is an alternating link on one or two unnoted components. And for the detail of the definition, see example for the on-class of classification of rational knots by Kaufman or Lambrou. And so it's look like in the picture for short. And the two-bridge links are also known in the literature as the four-plus or V-reflected and rational links. And a two-bridge link is either hyperbolic or a torus link. So a Euclidean cone structure on a link is a metric on the sphere with singular set L, which is a smooth Riemannian metric on the complement of the link in the sphere of constant curvature 0. And on the neighborhood of the x point of L has the expression in the cylindrical coordinates. That's so in the screen, the ds square and equal to dr square, which is the alpha over 2 pi r square and d theta square and dh square, where alpha is a cone angle, r is denoted the distance to singular locus, theta is the rescaled angle parameter around L, and h in R is the height or length parameter along L. When alpha is equal to 2 pi, this is a standard smooth metric of R3. And when alpha equal to 2 pi over k is for some integer k, this is the metric of orifles. A similar definition applies to the spherical and hyperbolic cone structures by replacing affine distance R by geometric functions in hyperbolic trigonometric functions of R. So we study the Euclidean structure on trefoil knots with a bridge, which is a particular case of two-bridge links with a bridge. In the case of ordinary trefoils, there are several works have been done. And trefoil knot 3-1 is a torus knot denoted by T23, and it is also two-bridge knot with notation K3/4 and or K3/5, depending on the orientation of the exterior. Johnston proved that the components of trefoil knots do not admit hyperbolic structure, but it does admit two other structures, namely h square cross product of h square and Euclidean space, and the universal covering of the Lie group PSN2R. Seifert and Weber show that the spherical space dodecahedron or Poincare homology sphere is a cyclic trifold covering of the three sphere branched over trefoil knot. So the orifol T1, 2 pi over 5 with singular locus, trefoil knot in the cone angle 2 pi over 5 has spherical structure. And by Dunbar classification, orbifold 2 pi 3, 1, 2 pi over n is spherical orbifold when n less than 5, and non-orbifold when n is equal to 6. And it's a PSL to R orbifold when n greater and or is equal to 7. Spherical structure on cone manifold C31 alpha is studied by defining Mednykh and Lilya, and the existence of Euclidean structure on trefoil nodes with a bridge was proved by Sokolova. And in the picture, show the manifold of the trefoil 3-1 with a bridge, and we denote by alpha and gamma. The alpha is the cone angle along the node component, and the gamma is the cone angle along the bridge, which colored by red in red. So we consider the trefoil node 3-1, and by writing the algorithm, we get a presentation of the fundamental for complement for trefoil nodes, which is by one in the so in the slide. You might see my my mouse. The holomy phi from pi 1 to isometric group of A3, carrying the generator S and T of pi 1 to the following isometry in A3, which is shown in the formula 1. A3 is a basic vector on the three-dimensional space, and S and T is a rotation matrices, and this is a matrices S and T, which in the notation of M, X, and Y, which dependent on the cone angle alpha and theta. Okay, so we brought that for the alpha greater than p over 3 and less than 5 pi over 3, and gamma is defined by the following equation. So the cone manifold 3-1 alpha gamma admit a Euclidean structure, and moreover there exists a 12-faced polyhedron in A3, which is a canonical fundamental set of the cone manifold 3-1 alpha gamma, and this shown in the picture fundamental set Fs. And I will show how to the idea how to construct that fundamental set. So we can represent the coordinates of the vertices Fs as follow: P1, P2, P3, P4, P5, P6 in terms of T, X, Y, and X, X, and so capital X, capital Y, and the Y and Z. And we know that the P5 is an image of P1 under the rotation tau. So we can find the parameter X, Y, so Y, Z, and T in terms of the cone angle theta and alpha, which is shown in the ecran, in the screen. And for that, we can have the fundamental sets is symmetric under the rotation S and T, and that implies that the M and X in the is kind of parameter in the coordinate. Then it's obeys some certain condition that's shown in the screen, and it is equivalent to the relation between alpha and theta. And furthermore, we have that the sum of interior dihedral angle along the axis of sigma P1, P6 is equal to gamma, and that means that the image of the element L, that's in the relation of the fundamental group in the cone-manifold 3-1 under homomorphism is to the isometry groove of E3 is rotation about an edge of 6 cone, the bridge by angle gamma. So it's well known from the linear algebra that for the choice of representation of L in the isometric group, we have the choice of this equal to 2 cosine gamma plus 1, and it will give us a formula for the gamma in terms of theta. And we know that the cosine of gamma is contained in the interval from -1 to 1. So that implies that alpha must satisfy the following condition for alpha. So alpha greater than pi over 3 and less than 5 pi over 3. And this is the idea of the proof of the theorem 1. And when we have the construct the fundamental set of the cone manifold, we can easily compute the Euclidean volume of the cone manifold C1 with the cone angle alpha and gamma, and easy, not quite easy task to computation. That's in the volume in Euclidean space. And I finished my talk here. Thank you for your attention.
Thank you. So are there questions from the audience? So what you did for trefoil knot, can you generalize it to say 2, n torus knots, or like any other knot?
So this is very ad hoc method to treat with some particular lot, because it gives different manifolds, cone manifold with different underlying space and singular set. We can generalize this into some family of knots, of course, yes, but it leads to more complicated computation, because the model in the Euclidean space or in any geometry is quite complicated in the presentation of the rotation group or the group fundamental group, and it's the obstacle to generalize this into any node.
Mhm. Yeah, all right, thank you. So if there aren't any questions, then we should thank the speaker, and we would end our session now. Thank you so much for everyone to attend the conference, today's talk.